Okay, so number 30 is asking us to determine whether or not this series converges, and if it does, to what sum. And to do this, we're going to be using the divergence test, which states that if the limit as n approaches infinity of a sub n does not equal 0 or does not exist, then the series diverges. So, what that basically, the case that will pop up a lot is you're taking the limit of your a sub n, and you get some value c, where c is not 0. That means it diverges. So if it's 1, negative infinity, whatever, negative does not exist, 500, whatever it may be, as long as it's not 0, then this thing diverges. Okay? However, this does not mean that f limit n approach infinity a sub n equals 0 does not imply, does not, big not, converges. And this is a common mistake. It's a logical fallacy. You're assuming the inverse, basically, which is not true. So, for instance, if you take limit as n approaches infinity of 1 over n, that's equal to 0. But 1 over n diverges. So that's the prime counterexample to this statement. This is not a true statement. So really, we're just looking for a constant or something. If it is 0, we have to move on to something else. So let's actually do it on this problem. And again, when taking limits of sequences or series, you can just use the real valued analog, and the limit is the same as seen in 11.1. So we're going to take the limit of that, and then the limit of this is the same as the limit of this. So dividing through by x squared on top and bottom. Oops, there's no x there. Top goes to 1, this goes to 1, this goes to 0, this goes to 0. So as x gets really big, 5 over x squared is 0, and then you can cancel 1x, 2 over x, again 0. So the limit is 1, so we're in this case. So it does indeed diverge, and you're done there. However, if it was 0, I do want to stress that does not mean it converges. We have to try other things.